In this video, I'm going to go over some of the prereq material for KNES 300. And by prereq material, I mean the prereq classes for the course, of course, the classes that you have to take and have completed at a certain level before you take KNES 300, and also some of the more technical material on the math and physics side of things that underlies KNES 300 and is part of KNES 300. On the math side of things, one point that I wanted to address is that most of you, maybe all of you, have taken a math placement test here at University of Maryland, which, depending on how you do on it, gives you credit for at a certain level of math at the university, and maybe you don't actually have to then take a math class, or maybe you don't have to take the math prereq course for KNES 300 or for your other courses. It is no secret around the university that that test is kind of a joke because it's really, really easy to cheat on it, right? They send you a link, you go take it on your own computer, wherever you want, and maybe you take the test, or maybe your friend who's real good at math helps you out, or maybe they even take the test for you. And that happens a lot, and that's not a surprise. We all know that happens, and it's not much we can do about it. If that's you, and I'm not getting into cheating or trying to turn anyone in or anything like that here, but if that's you, if you took that test and got placed at a level that is beyond your actual ability in math, that may seem like, at least in the short term, that you did something good for yourself. Hey, I don't have to take this math class. That's great. I don't like math. I can take some other class that I'd rather take. It's eventually, at least if you stay in the KNES major, that's eventually going to catch up with you. If it doesn't catch up with you before KNES 300, it's going to catch up with you in KNES 300. Because there you don't have to just have credit for the math, you have to be able to do the math. You have to have already at least a basic level of competency with fairly low level algebra and trigonometry and things like that. If you don't already have that mastery, and if you're struggling with doing the types of calculations that we do in that class, like solving the equations when the equation and all the numbers are given to you, you're going to struggle a lot in biomechanics, because that's not supposed to be the hard part of biomechanics. The hard part is supposed to be like reading a problem and understanding what equation is the right equation to use to solve that problem, and why that's the right way mechanically to be thinking about that problem. That's the difficult part about biomechanics. At least that's supposed to be the difficult part about biomechanics. If I tell you y equals some function of x, here's the value of y, here's the value of all the other things in this equation, solve for x, and that's hard for you to do, that's difficult for you, you're going to have a really hard time in KNES 300. And so regardless of what your transcript says for what your math placement level is and what math courses you may or may not already have credit for, if as I'm going through the slides that I'll cover here on what type of math and things like that are in KNES 300, and if you're looking at those and saying, gosh, I really don't think I actually know how to do that, at least on my own at a consistent level, then that's something that you need to address before you take KNES 300, because these types of calculations are part of KNES 300, but it's part of the prereq material. It's not stuff that we're going to reteach you in KNES 300. We're not going to teach you how to do basic algebra and basic trigonometry in that class. The mastery of that material on day one is the assumption for that class. That's why it's prereq material for that class. And so it's where you really need to sit down and have an honest conversation with yourself outside of whatever your math placement was. Do you actually know how to do this? If you do, you're going to be just fine in KNES 300. If you don't, you're probably going to struggle if you don't address it before you get into that class. Okay, let's take a little bit closer look at some of the prereq material, and I made some slides on this here. So KNES 300 has two prereqs. There's a anatomy and physiology prereq, B-Sci 201, so you'll all take B-Sci 201 before you take KNES 300, and there's a math prereq. You have to have taken at least one of, or credit for math 112 or 113 or 115, which is basically high school algebra and trigonometry. Recommended here, and I stress that it's recommended, not required, is a college physics class such as Physics 121, or we have an in-house class that Dr. Shim teaches sometimes, KNES 289P. Recommended here means if you are worried about the physics element in biomechanics, That's a good thing to be worried about. We do teach some physics in the class, and it's not a prereq that's required. And so I teach the physics in the class at an introductory level. I teach it assuming nobody has seen these things before. But nonetheless, physics is hard. Physics is a difficult topic, and a lot of students struggle with that material. And so if you are not confident in handling the physics in this class, the best thing that you can do to help yourself there is to take a physics class ahead of time. So take Physics 121 or some other physics class here at Maryland before you take KNES 300. It's generally been my experience that students in KNES 300 who have recently taken a college physics class like Physics 121 tend to do pretty well in the class. They don't necessarily like get an A or have an easy time, but the technical side of the class, or just the part of the class that involves like thinking like a physicist, is, I don't want to say it's easy, but it's more straightforward for those students who have already taken physics than those who haven't. Even if you've taken physics just in high school and haven't taken it in college, that's really the level of physics that we get into in this class. And so if you took physics in high school, and especially if you took it in high school and didn't struggle in it or did pretty well or even enjoyed it, that's typically sufficient background in physics for doing well in this class. Not saying it's a guarantee that you're going to get an A. I, of course, can't guarantee that. But it's rare in my experience that a student who has already taken physics in college or at least in high school really struggles in this class. The students who tend to have a really difficult time tend to be the ones who are not confident in their math ability and haven't taken physics even in high school, let alone in college. They tend to be the ones that really struggle quite a bit in this course. And so if that's you, if you're not confident in your math ability and you haven't taken a physics class at any level, even in high school, I would very much recommend addressing some of those things with the courses that you choose to take before you take KNES 300. So talk to your advisor about these things. What's a math class I can take that would help me be prepared for this course? What's a physics class I can take that would help me be prepared for this course? So it's not a prereq. You don't have to have taken a physics class to take KNES 300, but it's recommended as something that you give kind of a check on your ability of and your confidence in before you take this class. And it's something that a lot of students do take because many of our students are going on to postgraduate programs that require physics. And so even though if it's not a prereq for this course, depending on your post-graduation plans, it may be a course that you have to take anyway at some point. So why not take it before KNES 300 and set yourself up for success in KNES 300? Okay, let's take another look here. So the tools for math that we use a lot in KNES 300 and that you really need to already have a mastery of on day one to set yourself up to do well in KNES 300 are algebra and trigonometry. And so in high school, you probably all took algebra and probably all took trigonometry, but it might have been a while ago. And what do you need to know from those that's useful and necessary in KNES 300? Algebra is basically about solving equations. Okay, you have some equation y as some function of x, and we need to do things with these equations. Typically, we need to manipulate them symbolically, or we need to plug numbers into them to calculate the value of one of the terms in this equation. So an example of the level of complexity in algebra that we see in KNES 300 are these three equations here. Y equals some constant times x squared, y equals cosine of x divided by some constant, y equals x times some constant plus some other constant. If you can confidently take all three or any one of those three equations and solve them for x, then you're in good shape. And by solving them for x, I mean like if I gave you all of the numbers for everything here except for x, like if I told you the value of y and the value of a. If I said y equals 1 and a equals 2, what's x? If you could do that, if you could compute the value of x in that case, then you're in good shape. Beyond that too, if I don't tell you any of the numbers and I just say rearrange this equation or rearrange any one of the equations here for x, isolate x by itself on the left-hand side instead of y, and then get everything else here on the right-hand side. So solve this equation symbolically for x. So then you could plug in any arbitrary set of numbers and get the associated value for x. If you can confidently do those things with equations of this type of complexity, then you're in great shape for the type of or the level or scope of algebra that's involved in KNES 300. If you can't do those things with confidence, then you might want to think about taking a college math class that might brush you up on that or give you some additional skills in that area before you take KNES 300. Other type of math that we use in KNES 300, and algebra here is really the bulk of it. More at the conceptual level, less so in like actual calculations we do, is trigonometry, which is another high school math class you've probably taken or should have taken. Trigonometry, and I highlighted tri there, trigonometry is all about the lengths and angles of triangles. And there's one particular type of triangle that's really important in trigonometry and really important in biomechanics, and that's the right triangle. So all triangles, regardless of their shape and characteristics, have three sides and have three angles inside of them connecting those sides. A right triangle is a special type of triangle where one of those internal angles is exactly equal to 90 degrees, and that's this white angle that's highlighted here. These right triangles are important because they're special triangles that have special mathematical relationships when they're a right triangle. Like if I give you this right triangle and I give you the length of the hypotenuse there, the long side, and I give you this internal angle, then from that information you can calculate the length of these other two sides. The adjacent side here, the side touching the angle, is r times cosine theta, and this opposite side here, the side that doesn't touch that angle, is r sine theta. Okay. If I also give you the lengths here as just symbols like length A, length B, then the lengths of these three sides are all related to each other here by this Pythagorean theorem. R squared, the long length, is the sum of the squares of the two shorter lengths, a squared plus b squared. Okay. So that's just kind of a very superficial overview of trigonometry, but it's the type of trigonometry that you'll see in KNES 300. Not so much in doing calculations of these things, but like in the videos and examples and problems where I talk about like joint angles and segment angles and just conceptually what are these things. It's helpful to have an understanding at the high school level and at the early college level of these sort of concepts in trigonometry, so that you can see when I define a segment angle, oh yeah, that's a right angle, and that's why theta here is a correct definition of this sort of thing, and of what the orientation of this part of the body is, and things like that. So again, just useful information to have in your head that you already have a mastery of, so that when you see it applied to biomechanics, this isn't new to you, and you can focus on the biomechanics rather than focusing on the mathematics that underlie it. Okay, other element of math that we use a little bit of, again, more at the conceptual level rather than at the practical, like calculation level, is a little bit of calculus, and specifically differentiation and integration. Now, calculus is not a prereq for KNES 300. I would cast it in the category of physics, where it's not a prereq, but it's useful background information to have. Students who have taken, well, do I want to say this? Yeah, I think I do. I'm pretty confident in saying that I have, in my 7 years, almost 8 years of teaching this course, I have never had a student struggle in this class who took both college calculus and college physics before they took KNES 300. Again, that's not a guarantee that, take these classes and you'll ace KNES 300, but it's just been my experience so far in teaching the class that if it's somebody who did well in college physics and did well in college algebra, they tend to just sail right through KNES 300. It's not difficult for them because they can focus entirely on the biomechanics, and they don't have to focus on the math and on the physics. So calculus, after having said all that, calculus is not a prereq for this class, so I don't want to scare anyone here. Don't worry about it if you've never taken any calculus in high school or college. There are elements of calculus that are important for biomechanics and thus important for KNES 300, but we introduce them in KNES 300 at a very superficial kind of new learning level, assuming that you haven't seen these things before. The two key tools from calculus that are important in biomechanics are derivatives and integrals, or differentiation and integration. And these are really about, these tools as they apply to mechanics and biomechanics, are really about looking at how a variable is changing or fluctuating in time, and what this tells you about other variables. So an example of how this applies to biomechanics is, this is a graph of the velocity of somebody's body, their center of mass, during a stride of running. Okay? So time here, the time during the stride here on the x-axis, and the velocity of the center of mass on the y-axis. Okay? The rate at which this velocity is changing, whether it's decreasing here or increasing here or not doing much here at these peaks, and how quickly it's doing those things, like whether it's decreasing quickly or slowly, or increasing slowly or increasing quickly. That's the slope of this curve, the rate at which it's increasing or decreasing its value with respect to time. And that's the derivative of this curve. The derivative is the slope of velocity here with respect to time. That derivative, velocity versus time in mechanics, is acceleration, the rate at which something is speeding up or slowing down. Like in your car, if you slam the gas, you speed up, and if you slam the brakes, you slow down. That's acceleration and deceleration. So the slope, or the rate at which this blue line is increasing or decreasing, tells me something about some unmeasured mechanical variable here. From these velocity data, I can glean the acceleration of this person, even though I didn't strictly measure acceleration. Integrals are a little bit more complicated. Integral is about like the area under this blue curve, or the area, if you imagine like a line being drawn here horizontally all the way through 0, and then think about like the area between that horizontal 0 line and this blue line here. So imagine like progressing here from left to right and like kind of tracing out the area between that blue curve and between the 0 axis there. That as the size of that area increases over time as we proceed from left to right here, that's the integral of this curve, the rate at which the area under the curve is accumulating. And that also tells me something about some unmeasured mechanical variable here. That would tell me something about the position or the location of this person's center of mass. So we can use these basic principles from calculus, and we do this largely at a conceptual level in KNES 300. We don't actually get into like calculating these things like numbers for it very often. But these things can conceptually tell us something about unmeasured data and unmeasured variables. I can learn something here about position and acceleration just from measurements of velocity, even though I didn't actually measure position and acceleration. I can learn about them from this curve of velocity here. And so that's really where calculus appears in KNES 300. It's not a prereq for KNES 300, but again, it's helpful to have some exposure to those things so that when you see them in class, you have some confidence. You say, oh yeah, I've seen this before. I know what that is. I can understand that, rather than getting worried about learning it on the fly and also trying to understand the biomechanics on the fly. Okay, other terms that we use from math, and this kind of delves into physics a bit too, is the distinction between vectors and scalars. A scalar is a variable that's defined just by one piece of information, just a magnitude. An example would be like if you go outside and you go for a run and you ran 5 miles, that's the distance that you ran, and that's a scalar piece of information, a scalar variable. If somebody asks you how far you run, you just say 5 miles. They don't necessarily need to know like what direction you ran in, where you ran, what hills you went up and down to know how far you ran. You ran 5 miles. That's the distance that you ran. Those other variables are relevant, right? That might affect how difficult the run is or how fast you're able to run if you have to go up a bunch of hills or on rough terrain or twist and turn a lot. But the distance that you ran is 5 miles. It's like if you trailed a string behind you on the ground while you were running, and then at the end went back and picked up that string and stretched it out and measured how far it was, that'd be the distance that you ran. You don't need any other information to say how far you ran. The vector example there, the vector like counter to that, would be a vector is a variable that's described by multiple pieces of information, a magnitude and a direction, and in some cases a third piece of information, a point of application, but always a magnitude and a direction. The example there for my running analogy would be, suppose you go out and you do a run, and you start at your house or at your door, and you go out and you run, and then you end up back at your door. Okay? The distance that you ran is the 5 miles. That's the length of the string or the length of the path that you went on. Your displacement is actually 0, which kind of sounds like you didn't go anywhere. And you're like, wait a minute, I just got screwed. I just ran 5 miles, and you're telling me I did 0. That's not fair. Your distance was 5 miles. Your displacement was 0, because displacement cares not just about the magnitude of how far you went, it cares about the direction that you went. And when you're running these 5 miles, you're constantly changing direction, making turns, yada yada. You start at your door, and then you run around, and then you end up back where you started, back at your door. So from a vector perspective, you didn't go anywhere. You started somewhere and you set out, but then you kept changing direction and kept turning and ended up back where you started. Okay? So your displacement was 0. You stopped and started in the same spot if we consider the direction that you went. So distance, scalar, 5 miles. Displacement, 0, because you stopped and started at the same spot. Okay? So again here, not things that you need to have like a mastery of, and these are really not things that are all that super important to do well in KNES 300, but it's things that come up in class and that it's helpful to have some familiarity with in my experience ahead of time. Students that already have seen these things before, whether it's in high school math classes or college math classes, high school physics classes, college physics classes, tend to do better in the class than students who haven't seen these things before, if this is all new information to you. So if you're seeing these things that I'm showing here in class and you're like, man, I haven't seen that before, I'm worried about that, I'm not familiar with that, that's not something you should necessarily be worried about or scared about, but it's something you should think about addressing ahead of time before you take KNES 300. Maybe talk to your advisor about what's a math class I could take, what's a physics class I could take that would prepare me to learn some of these things and to kind of hit the ground running in KNES 300. Okay, some tools from physics or some topics from physics that are important for KNES 300. And this information here is again kind of a reality check for you. As I'm going through these terms and this material, these are ideally things that you've heard of before, that you have some superficial familiarity with already. If it's not, it's again been my experience that students that don't know already about these things or are intimidated by these things tend to struggle more often than not versus students who are not intimidated by these things or who are familiar with these things already. And so again, if these are things that aren't familiar to you, you don't necessarily need to be super scared about it, but you do need to think about, well, maybe I should take a physics class before I take KNES 300. Maybe I should set myself up to do well in KNES 300 by taking my physics class ahead of time. Okay, position, velocity, and acceleration. We already talked about these a little bit. These are the 3 essential kinematic variables for describing a body in motion, whether it's a human body in motion or just a body in general. Kinematic here is a fancy word for movement. So going back to my first video, kind of the core of kinesiology, it's all about movement of the body. And position, velocity, and acceleration are the 3 key movement-related variables in physics and thus in biomechanics. Position is where your body is in space. Velocity is the rate at which that position is changing, and acceleration is the rate at which velocity is changing. All 3 of these things are vectors, meaning they're defined by both a value and by a direction. There are scalar versions of the first 2. There's distance, which is just the magnitude of your position, and there's speed, which is just the magnitude of their velocity. But broadly speaking, these kinematic variables up here are vectors. We're concerned both with the value of them and with the direction of them. An example I can give you here is, let me pull my video up. Here's my phone, my cell phone, and let's suppose I take it and I fling it across the room. Okay, I fling it with my hand and it's airborne and it's flying across the room. Okay? Suppose it's flying through the air here, and I have magic powers, and I snap my fingers, and I freeze it in space here in this room. And I say, okay, I'm going to snap my fingers again, and that's going to unfreeze this thing, and I want you to tell me where is it going to be when I unfreeze it a short time into the future. What pieces of information about the movement of this phone do you need to know to make that prediction accurately, to tell me once I unfreeze it, where is it going to be a short time into the future? Okay. Well, at a minimum, you'd have to know its position, right? If you don't know, if it's just blank here and I tell you, okay, I'm going to unfreeze my cell phone, where is it going to be in the future? You have nothing to go off here. You have no idea, okay? So minimally, I have to tell you, like, what is its current position? Where is it right now? If you want to tell me with any degree of accuracy, like, where is it going to be in the future, okay? If I just give you its position, though, you're still going to be doing a lot of guessing when I unfreeze it and ask you to tell me where is it going to be a little bit into the future. To know where it's going to be in the future, you have to know not just its current position, but its current velocity. Okay, is it moving this way? Is it moving that way? Is it moving that way? Knowing those 2 pieces of information, where is it right now and where is it heading, you could probably tell me with pretty good accuracy, at least a short jump in time into the future, where my phone is going to be in space. And we can extend that with other kinematic variables. If I give you, say, also the current acceleration of this thing, mechanically you could then predict even more accurately, or over an even longer period of time, where is it going to be a little bit into the future here when I unfreeze it after freezing it in the air here. So just an example about how these pieces of kinematic information about the movement of something are related and can help us describe the movement of it and predict things that are interesting about the movement of bodies. Okay, so we can relate position and velocity and acceleration to each other with calculus, like I described earlier. For example, we can take derivatives of them with respect to time and calculate these other variables. We can take integrals of them with respect to time and calculate these other variables. For example, if I give you the position of a body with respect to time, the derivative of that position versus time gives you the velocity, and the derivative of that velocity gives you acceleration. Okay? In the other direction, if I give you velocity and you integrate it over time, that gives you position. Oops, sorry. And if I give you acceleration and you integrate it, that gives you velocity. Okay? So again here, these are helpful things to already have at least some familiarity with, to have already heard of before, like knowing what position and velocity and acceleration is, knowing what a derivative is, knowing what an integral is. These aren't things you need to have a mastery of to do well in KNES 300, but it helps to have heard of these things before. It helps to have already taken a course that covered some or all of these things before. Okay, so that's kinematics. That's a fancy word for motion. The other kind of half of mechanics and biomechanics is kinetics, which are the forces that cause motion. The key central variable in kinetics, and I would say the central variable in all of physics, is force. And this is kind of a wishy-washy definition in physics where it's an action or a physical interaction that tends to change the motion of the body. And often in biomechanics and in physics and in mechanics, we'll be looking at all of the many types of forces that act on somebody's body, like gravity, for example, and sum them up. And that sum of forces is the source of our favorite equation, or the most famous equation in physics, which is F equals ma. If you sum up all the forces acting on a body of mass m, then that sum of forces equals the mass of the body times the acceleration of the body. And then from my slide here on the previous page, if I know acceleration, then I can compute velocity and I can compute position. I can compute all my interesting information about the movement of the body. So this is really what Isaac Newton, kind of the godfather of classical physics, came up with that was so brilliant. It's a very simple, short equation that relates the forces that cause a motion to the motion itself. And from this, we can basically get all of the kinematic information that we need to describe the motion of the body from this simple equation relating the cause of motion to the actual motion. Work is another key kinetic quantity in physics and in biomechanics. Work is a force that's applied to something that displaces that something. An example here would be, if I go to my video, here's my phone, and I'm holding it in my hand, and I'm going to apply a force to it and displace it against gravity. Okay? That was easy. My phone doesn't weigh very much, but I did a little bit of work on my phone because I applied a force to it, and that force caused some displacement of it. Okay, so I did a little bit of work with my muscles and my arm muscles, raising that phone up against gravity there by doing work on it, by applying a force to it and also causing displacement of my phone with that force. On the other side of things here, here's the wall of my kitchen here. And so the wall, one of the main structural walls of my house, I can go here and I can push and push and push on this wall all day long with all my might. And it feels like I'm doing a lot. I'm doing a lot of effort. And I am. I'm exerting a lot of effort. I'm burning some energy. I'm producing a lot of force. But I'm not performing any work. Okay? Why not? Because work is force times displacement. So it doesn't matter how much of this you produce if there's none of this. You can produce all the force in the world, but if it doesn't cause any displacement, you didn't do any work. Okay? It's kind of like work equals force times displacement. Doesn't matter how big force is, any number times 0 is still 0. Okay? So no displacement, no work. Doesn't matter how much force you produced, you got to displace something, you got to move the something to actually do work on it. Okay, sometimes, and especially in sports applications, it's not so much that important how much force you can produce. It's not even that important how much work you can produce, but being able to produce work quickly is really important. And that's where power comes in. Power is the derivative of work with respect to time, or the rate at which work is done. And so think about not just producing work at all, but think about producing that work quickly, like lifting the weight up in the air, not just accomplishing that, but lifting it up in the air quickly, doing a lot of work on the weight in a short amount of time. That's what power is. Okay? Power lifting, the sport, I think is actually poorly named because that's really more about work, right? Moving the weight at all, whether or not you move it fast or not. Olympic lifting, where they're doing like clean and jerk and snatch and stuff like that, that's a lot more about power. That involves more of a speed and more of a power element. Or like field sports, like football and soccer and baseball, are much more about doing work and doing work quickly, so involving lots of power. Okay? So power is not, I would say, less central to physics than force is, but is a really important variable in biomechanics and is particularly important in sports applications. The ability to not just do work, but to do work quickly with your muscles. Okay, last but not least, here is energy, and energy is closely related to work and power, and you can think of energy as kind of the capacity to do work. An example that you might be familiar with, depending on what courses you've taken already, is human food energy. Okay, why do humans need to eat food? Well, there's a nutrition aspect, but there's also a physics aspect. We eat food to store food energy in our body that we can then convert through our muscles to mechanical energy, to work that we perform on our bodies themselves to move them against gravity, or on objects that we're interacting with, like to move things around the world that we interact with, whether it's exercise, moving weights, or moving a chair, or taking a drink, or whatever. All of that involves using our muscles to perform work on our body and to objects that we interact with our body. And we don't get that work for free. We have a cost to it. We consume metabolic energy inside the body to power the muscles to convert it to that mechanical energy, to that work that we do with our bodies on the body itself or on objects that we interact with. There's lots of different types of energy in physics and in biomechanics. There's chemical energy, which is a type of food energy. There's mechanical energy, there's thermal energy. All three of these are important in muscles. You might have heard, if you've taken a physics class, about the notion of conservation of energy, which is this idea that a closed system has a total or a certain total amount of energy that we can't create or destroy, but we can move it around. We can transform it from one type to another. And this is a really key principle in physics and mechanics and biomechanics, and is really important for explaining things related to why humans move the way that we do. Why does everybody kind of walk in the stereotypical human type way? Why do people run the way that we do? Why do we perform exercises in the gym the way that we do? Or what's a good way to perform those things? Conservation of energy can give us some really keen insights into topics like that when we apply it to biomechanics. Okay, that was it for my slideshow here on kind of prereq material and prereq knowledge for biomechanics. Again, I want to emphasize the formal prereqs for this course are anatomy and physiology and the math requirement. To take this course and to do well in this course, you don't have to have taken college physics and you don't have to have taken college calculus. It's been my experience that students who nonetheless have done those things tend to just sail through this course, especially if you take college physics and do well, and take college calculus and do well. I've never had a student who struggled in biomechanics under those circumstances. There have also been plenty of students who have done really well in biomechanics who haven't taken college physics and who haven't taken calculus. So I'm not saying you have to take those things if you want to do well in this class. There's historically been many students who haven't taken those classes and have done just fine in biomechanics and have learned a lot in biomechanics and gotten very good grades in biomechanics. But if you are nervous about this class, if you're worried about doing well in biomechanics because you're not confident in your math or you're not confident in your physics, now in your early years at the university, in your early years in the program, is the time to do that. Address that not by just worrying about it, but address it by taking courses. Take a physics course, take a math course, brush up on these things, and prepare yourself to do well. Set yourself up to do well in a class like KNES 300 and in your other core classes that involve a little bit of math and a little bit of physics. Okay, that is it for this one. In the next video, I will talk a little bit about a specific tool that we use for math and physics and biomechanics, and that is a spreadsheet.